Alright, and welcome back. So in this video we're going to be going over section 14 of Munkres Topology. Quick little disclaimer, if you haven't seen any of the other videos, I am not a teacher for this course. I myself am continuously learning. I'm actually in the class right now trying to learn about it, and these just kind of help me learn along the way, and maybe we could learn something together. So we're going to be going over section 14 of Munkres Topology, and it talks about the order topology. So we first start off with a pretty simple definition over here, and then we'll get to a more a more in-depth definition down here. So first we say if X is a simply ordered set, so simply ordered means that you can compare numbers with one another. So in this example, like A is less than B, there's no ambiguity between, which value can come before another value, right? So we say there is a standard topology for that set if it is simply ordered, defined using the order relation. So the order relation is an equivalency relation. It's just a specific form of an equivalency relation, and it just holds that A is less than B, for some A or B, right? And we call that the order topology. Now, jumping into this next point down here, there are four subsets of X that we call intervals, determined by A and B. Now, reading this should be pretty familiar to most of you watching, how we're defining this, but we want to be pretty thorough in how we set up definitions, especially once we start getting down to more topologies down the line. It helps to kind of like keep these in mind. Because once again, we need to have like this idea of openness and closedness in topology is like a very important thing. So the first one is the open interval AB. So this is defined as the set X. So these are all the numbers between A and B. We have a half open interval for AB, where B is included but A is excluded. A half open interval where A is included and B is excluded. And then we also have the closed interval where both of my endpoints are included. So once again, that shouldn't be, I wouldn't say that's new news to us here, but let's look at this definition over here, right? So we say let X be a set with a simple order relation. So for example, like 1, 2, 3, 4, 5 would be a simply ordered set X. Assume X has more than one element, because if X is just a singular element, well then the order relation doesn't really apply. Off a technicality it would, but that's not what we're interested in, right? So let a collection B be the collection of all sets of the following types. So we need to have all open intervals in X. We need to have all intervals of the form half open interval A sub aught B, where A sub aught is included and B is excluded, where A sub aught is the smallest element, if any, of X. That's if we just happen to have a smallest element. There doesn't have to be a smallest element. And it's the same for the third point below. All intervals of the form A B sub aught, where B sub aught is included and A is excluded, where B sub aught is the largest element, if any, of X. So in the particular example that I gave, where I said 1, 2, 3, 4, 5, right? Well, that set has and actually, let me go ahead and just write that out, actually. So, like, let's say I have a set X, and that set is defined as 1, 2, 3, 4, and 5. Well, I have a smallest element and I have a largest element, so I would need to ensure that 2 and 3 apply here. So my basis would wind up being the collection of open intervals inside of here, where my open intervals would be filled with positive integers in this particular case, but I need to make sure I need to include those endpoints so that I cover all of X. The other point to make here is, sorry, let me go back here for a quick second. The other thing I wanted to kind of point out is the reason we say if any is because we can have infinite, right? So like, let's just say, for example, we're looking at R. Well, R is infinite, right? Well, I don't have a smallest element. As long as I'm not bounding R, I don't have a smallest element and I don't have a largest element, so I would just be focused on the open intervals of A and B, for instance. All right, so we do need to first check that this collection B does satisfy the requirements for a basis and therefore does form a topology. We do need to say that, well, I guess the first thing you can look at here is that every element of X is going to be in at least one subset of at least one set of my collection, right? So if I have my collection B, then that's a collection of all sets. Sorry, I'm running around in circles. So we have B, which is our collection, right? Well, X has to belong inside of there, right? Because we're basically saying that by definition, B has to, cover all of X by this construction. So X will be included in there, right? The smallest element will always lie inside of this guy. The largest element will always lie inside of this guy, if need be. Once again, doesn't have to. And every other element is going to lie within this kind of interval, right? Now, one more thing to note is that the intersection of any two sets of the preceding types is again a set of one of these types or is empty. So if I were to intersect these sets, they either give them back something that would fit inside the set or another one of these sets, or it would just wind up being empty. One thing we can define is just kind of like hopping back to some examples over here. R is a standard topology. We can define it as an order topology as well, as long as we just give it the order relation. But let's go ahead and consider another case. So let's consider R with the Cartesian product of itself, right? So that's going to give me these points at, what we're kind of familiar with, like our x, y's, right? Now this is kind of a little bit of a not so elegant way to write it, but you get the notion here, right? If we were to apply what's known as the dictionary order, so we apply something called the dictionary order, right? So what the dictionary order is stating is that if I have, let's say we have the points of here, let me draw it out a little bit. So let's say like this is my standard x-axis and this is my standard y-axis. What the dictionary order is saying is that first I'm going to order on my x's and then I'm going to order on my y's, right? So if I have x1 comma, let's say I have 2 points, x1, y1, and x2, y2. So the dictionary order is first going to look at these guys right here. So we're looking to see is x1 less than x2, and these are arbitrary, so you can look for x2 smaller than x1 as well. And if x1 equals x2, then we look for y1 being less than y2. So visually speaking, this is going to kind of look something like this, where we're kind of coming up and over as we kind of take our steps along, eventually till we get to a point of stopping. So we can create another visual from this. Like let's just say I have a set defined as A cross B and C cross D. And I can create just a simple visual for this. So let's say that I have an open set that goes like this, where this is my A cross B and this is my C cross D. So you kind of get the intuition of like how this is moving along, right? Another example we can give is the natural numbers or positive integers. They do form an ordered set and they do have a smallest element, right? So the order topology on the naturals is the discrete topology for every 1 point set is open. So if n is greater than 1, we get the 1 point set. sorry, let me go ahead and write this out. So we have the naturals, right? Or you may see it written as like z positive. You may see like the plus down here as well, but not that big a deal. We can give that the order topology. We can have another set, get a little funky with it. So let's take the Cartesian product of a finite set with the naturals. And we will assign this the dictionary order as well. Sorry for the bad handwriting. Now, in this particular instance, the order topology on this set is actually not the discrete topology. Most of the one-point sets are open, but there is an exception, and the one-point set B sub 1 must contain a basis element about B sub 1, and any basis element containing B sub 1 contains points of the AI sequence. So we can think about this as 1 cross n is my AN, and 2 cross n is my BN. Well, I'll have A1, A2, dot, 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 and then eventually I get to some stopping value, right? And then I'm going to have to make this jump. So essentially what I'm doing is I'm making, and this is a semicolon, not a J. So then I have to make this jump over here to B2. So there's some sort of jump that needs to happen. And visually speaking, what I'm saying is I'm going to keep going up, 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 up right here. And then eventually I have to jump all the way back down and then start over here from this B, right? So if this is 1, this is 2, some jump needs to happen, right? Okay, let's go back to our definitions. Definitions here, so just open rays and closed rays. Once again, this should be very familiar. Nothing that should be shocking here about this definition. Now, the term open does suggest that the open rays in X will be open sets in the order topology, and they are, right? But something special about the rays is that they will form a subbasis for the order topology on X. Basically because the open rays are open in the order topology, the topology they generate is contained in the order topology. On the other hand, every basis element for the order topology equals a finite intersection of open rays. So the interval AB is the intersection of an open of a ray negative infinity to B and A to positive infinity. While the smallest and largest elements, if they exist, are themselves just open rays, right? So the topology generated by the open rays contains the order topology. So it's another way to rewrite the order topology, essentially, right? That's pretty much it for the order topology. This topology is actually like fairly straightforward in my opinion. Not a whole lot to talk about it. It is pretty intuitive. It's very, very close to the standard topology. Very, very close. It's pretty intuitive to start getting a grasp on.